All right. Well, this is part 5 of dynamics. This is the last part. This video, you're going to learn about tension, Atwood machines, and equilibrium. At times, this is a little complicated, so hang in through it. Pause it when necessary. Rewatch it if you need to. Okay, so let's just talk about tension first. So tension is a force that's transmitted through a rope, string, a cable, or wire when it is pulled tight by forces acting on opposite ends. So in this diagram down at the bottom, we have an applied force to the right, and we have a rope that's between the two masses. The whole system will move together, but there will be this tension in this rope that's between the two masses. It's directed along the whole length of the string or wire, and pulls equally on the objects on the opposite ends of the wire or rope. We're going to calculate the tension between the objects that are accelerating, and we're going to, of course, use Newton's second law to do this. Okay, so here's a typical problem. We have two masses sitting on, we're going to use this as a frictionless surface. There's a rope between the two masses and an applied force of 50 newtons to the left. And we're going to find the acceleration of the system. The best way I know how to do is we treat the masses as one. So we just basically put them together, and we use Newton's second law, which says the sum of all forces equals ma. So essentially we're going to ignore the tension of the rope between the two at first. We're just going to put them together. So we have 50 newtons pulling to the left, and then we have a total mass of 20 plus 10 times the acceleration. So as simple as that is, we get the acceleration of 1.7 meters per second squared. So it's as if it's just one all mass, because it's all moving together. Then we're going to calculate the tension of the rope between the masses. We do this by isolating one of the masses, and then we use Newton's second law on the individual mass, because now we know the acceleration of each of the masses. So first I'm going to look at the left one, the 20 kilogram. We have 50 newtons on the applied force to the left, and then we have this tension because we've isolated it from the other mass. So to use Newton's second law, sigma F equals ma. We have the two forces, 50 to the left, tension to the right. So we're actually going to subtract those two. So I have 50 minus T, and T stands for the tension force, of course. And that equals the mass now is only 20, because we isolated it, and times the 1.7 meters per second squared that we calculated of the system. We do a little algebra. We move the 50 over with the 20 times 1.7. If you can see that what we actually do is I'm going to move the tension over here to make it positive, and then subtract this from the other side. So it's 50 minus the 20 times 1.7. So that comes out to 17 newtons of tension between the two. Just to show you that it works for the other mass also, I'm going to do the same thing. So I isolate the mass. This time I only have one force, which is the tension force that's pulling to the left on the 10 kilograms. So I use Newton's second law. The tension, that's the only force, equals the mass times the acceleration, and sure enough it comes out to 17 newtons, just like the other one, because these two tensional forces are exactly the same. You don't have to do both of these calculations. You can choose one. Hint, this one of course only had one force, so the math was a little easier because we didn't have to deal with subtracting the two forces in order to get that. So that's very simple. Find the acceleration, find the tension. Now, a twist now, and that is if we take the same system, but now we put it on a friction surface, and with a coefficient of friction is 0.1. That, of course, is the kinetic friction because we're assuming that it's already moving. So now we have a friction from the 20 kilogram mass. We also have a friction from the 10 kilogram mass. So we're going to do the same thing, except I'm going to put the two blocks together and then just call it one friction because I'm trying to find the acceleration. So there's the applied force. We just pretend that they're next to each other because we're not worried about this tension at this point. And then I sort of combined the frictions. So we treat it as one mass, F equals ma. We now have two forces. We have the applied force of 50 newtons to the left, and then opposing that is the friction. So that's going to equal the total mass because I've combined them together times acceleration. So now we plug in for the friction. We mu the mass of the total mass, which is the 20 plus 10, and times 9.8 equals 20 plus 10 times the acceleration. We do a little math first. So I'm adding the 20 and 10 together in both cases. That's the only thing I did. Substitute 9.8 in for G and 0.1 in for the coefficient of friction. I then do this calculation, which comes out to 29. So I'm going to subtract 50 and 29 divided by 30. So it's 21 over 30, which is 0.7 meters per second squared. Pretty straightforward, just about like the last one. We just have to throw in the friction force that's happening. So to find the tension between the ropes, now I'm going to isolate one of the masses. It doesn't matter which one. I don't really have room to do both of them, so I chose to do the one on the right. It has this tension, which I'm looking for, and the friction on that block. And then, of course, we already calculated the acceleration. So I use Newton's second law again. I now have tension. Because the system is going to the left, then I'm going to treat the T as larger than the frictional force, which, of course, it would be, or else it wouldn't move. So then I'm going to solve first for, I'm going to plug in for friction, mu mg, equals ma. I now will plug in the numbers. 0.1 is the coefficient, 10 is the mass of this object, 9.8 is the acceleration due to gravity, and the mass, now I'm not using the 30 anymore because I've isolated it, so it's just 10 times the 0.7 that I calculated as the acceleration of the system. I do the multiply and then subtract it from that, and because I didn't have enough room. It comes out to 16.8 newtons. So it's a little bit less than the 17 newtons that I had before. And the reason is because the acceleration is so much less. So a little bit trickier because we have friction, but still doable. If you would have chosen the 20 kilogram instead of this 10, then you would have had 50 and then T over here. So the sum of all forces would be 50 minus T, and then you do the algebra for that. Not too bad. So that's a block on a horizontal. So now, okay, so here's another type of problem. This apparatus is called an Atwood machine. It is simply just two masses connected by rope. The rope going over a pulley. The pulley has no friction, and maybe we'll deal with that later. But right now we're going to call it a frictionless pulley. And this mass slides on the horizontal, and this one's hanging down. So this problem happens to be a rock with a mass of 5 kilograms hangs on a rope over a pulley that's attached to a suitcase that has a mass of 10 kilograms. If there's no friction, what is the acceleration on the system? Obviously no friction from the hanging mass, but no friction from the suitcase either. So this one, I'm going to do the same sort of thing as I did the last type of problem. I'm going to take the two masses and just treat it as one system. So now we have the suitcase and the rock all moving towards the right, and the applied force is going to be the weight of the 5 kilogram mass. So I set up Newton's second law, sigma F equals ma. I substitute in for the mass. I add the two masses together because the whole thing is going to be accelerating at the same rate. So the sum of all the masses is equal to the mass of both masses times the acceleration of both masses. The only force causing the motion is the weight of the 5 kilogram mass. All right, so that sigma F turns into the weight of the 5 kilogram mass, so I subscripted 5 so we can tell the difference. And this, of course, is the mass of the 10 plus the mass of the 5 is equal to acceleration. So it's simply said, put in the numbers. 5 times g is 10 plus 5 times acceleration. 5 times 9.8 equals 15a. 49 equals 15a, and now we put the number in there and do the calculation, and we get 3.3 meters per second. So the whole system is going to be falling at that rate. True, it looks like it's in free fall, but because this is dragging this behind, then this is not 9.8. We're now going to calculate the tension in the rope. To do that, I'm going to once again just isolate one of the masses. First, I'm going to isolate the one up on top. The only force on it, remember there's no friction. The normal force and the acceleration, or the weight of that, has no bearing on the tension. So I can simply use Newton's second law, replace the sum of all forces with the tension, and that equals the mass now of the 10 and the acceleration that we just calculated. So it's just simply 10 times 3.3 will be the tension, or 33 newtons. As a contrast, if you choose to use the other mass, now we have two forces on it. We have the tension, which assuming we don't know it's 33, but we have the tension that we're looking for, and then the weight going the other way. Yes, it's down and it's up, but I'm just drawing it as though it's left and right because it's easier to draw. Same process, sigma F equals ma. Now, though, I have to take, because the system is going to the right in this picture, down, which is to the right, now I'm going to put that force as first. So weight of the 5 goes first, minus the tension, is equal to the mass of the 5 times the acceleration that we calculated over there. Doing the algebra and putting the numbers in. So essentially I brought the t over for positive. I brought the ma over there as a subtract. So that's why it's 5 times 9.8 minus 5 times 3.3 for a total of, once again, 33 newtons. So either one of these you can do. To me, that one was easier to do because it didn't require me to do all this algebra. But just showing you that you could use either mass in order to get that tension force. Okay, so let's take that problem. Now we're going to twist it a little bit, and of course we're going to put friction involved here now. So we have the coefficient of friction as 0.2. Now it will only be affecting the mass that's on the horizontal because, of course, there's no surface for that. So we just do the same sort of thing, but now we have to throw in this friction from the 10 kilogram mass. Once again, I put them together. I just ignore the tension for right now because I'm looking for the acceleration. Sigma F equals ma. Once again, the sum of all forces equals the total mass and the acceleration of both the masses. So now I put the force of the 5. It's really the weight of the 5 minus the friction, because this is the one that's doing the pulling and this one's doing the opposing. So I subtract them. That equals the total mass times the acceleration. I now plug in put the smaller numbers in there. So this is the mass of the 5 times g minus the friction on the 10. So it's mu, mass of the 10 times g, equals the total mass times the acceleration. Now put all the numbers in there. Well, almost all the numbers. 5g, which is 5 kilograms times g, and I replace the mass of the 10 with the 10 kilograms and the 10 and the 5. Putting all the numbers in now, I have put the 0.2 in there that was given in the problem, and so now I end up with on the left 29.4, 15 on the right. I then take acceleration equals 29.4 divided by 15, which is 1.96 meters per second. Different than we had before because now we have this friction to deal with. So to calculate the tension on the rope, we now isolate one of the masses. I'm going to choose the suitcase, so I have the friction on the left, tension on the right, and do the same. Sigma F equals MA. Because the system is going to the right, then the tension comes first, and subtracting out the friction. And now because we've isolated this mass, we have the mass of the 10 times the acceleration that we found. We're going to move that friction over, plug in the numbers, 0.2, that's the mu, times the mass of 10 times 9.8. So that's the formula for friction, plus 10 times the acceleration that we found there. The tension is 39 newtons. Yes, a little bit more than the last problem because, of course, we have friction to deal with. Without going through the whole problem, oh, sorry about that. Yeah, you could actually do the other one too, like the previous, but I'm not going to do that. Okay, so the next concept is called equilibrium. First, a definition of equilibrium, and that's when an object is not moving, or it's static. And because of this, it's static, the net force is equal to 0. That means if we add up all of the forces, we get a 0 resultant. So here's an example. We have this sign that's hanging by these two ropes. The sign is stated as 85 kilograms, and what we're going to calculate is the force, the tensional force on each of the ropes. Logically, we have weight going down, and we're going to calculate the tension. We're going to subscript the force with a T to call it tension. And so in our calculation, we know that the up forces are equal to the down forces. We happen to have two up forces, so we're going to call that 2 times tension. So we'll calculate a single tension is equal to the weight of the sign. Quick algebra, multiply both sides by half. So logically, you probably already figured out that, well, the tension of each of those is going to be half of the weight. There's no acceleration. Remember, net force is 0. So we don't have to deal with Newton's second law because it all comes out to a 0 acceleration. Now we plug in the 85 times 9.8. So the tension on each rope is 416.5 newtons. So what we're showing here is that the force down, which is the weight, is equal to the sum of the two forces going up, and all the forces add to 0. Pretty straightforward. Sometimes it's difficult to figure out what to do on these problems, but use your logic. It makes a lot of sense. Now, what if we take that same sign and we put the ropes in the middle of the sign, and now we form this angle? We have a 62-degree angle formed from the sign to the ropes. Now we're going to calculate the tension. Intuitively, I want you to think right now whether we're going to get the tension as more or less. Pause. Okay, let's see what happens here. So we've got the weight going down, obviously. We know that the forces all add to 0 because this object is not accelerating anywhere. We label the tensions. We're going to note that they're equal, so they both have a variable of t, because they both have the same angle, and assume that this is in the middle of the sign. But here's the trick. The opposition to the weight are going to be the two components on the tension forces. So we call that the y component of the tension, Ty, that plus that. So the sum of the two y forces are going to equal the weight. What's that going to do to our result? So once again, we have the up forces equal to the down forces. And the up forces are two tension y component. So the only difference from the last problem is now we're looking at these y components. Well, do the algebra. 1/2 mg did the same thing, but now let's substitute in for Ty, and of course, because Ty is opposite of 62, then we substitute in there the tension, the hypotenuse, times the sine of 62 is equal to 1/2 of the mass of 85 g 9.8. What's that going to do to the total? So now we have tension equal to, I did the math here, 1/2 of 85 9.8 is 416.5. Actually, remember that from the last problem, but now we're going to divide that by the sine of 62. Does that make it more or less? Well, it makes it more. How about that? Why is it more now? I want you to think about, why did we get a tension that's more by simply putting an angle on there? The answer to that would be that this tension is more because not only is it a combination of the up opposing the down, so it's the up force opposing the down, but it's also holding it with the x component. We could calculate what the x components are. They're obviously equal to each other, but there's a force there that's holding it sideways. Be interesting to think about what if we make this angle less and less and less, so the tension is really shallow there. You think that's going to increase or decrease the tension on the two? We'll think about that. So here we're showing once again that the sum of the two angles, now remember these are vectors, so we added them as vectors. So you can see once again this is why it's going to be more. It's no longer straight up on both of them, but now it goes off to the side. But all that equals to 0. Same as before. Okay, so that was we learned about tension. We learned what an Atwood machine is, and then we talked about equilibrium here. So expect that on the next quiz. Okay, well, thanks for listening. If you have any questions, make some comments on the video. If you want to ask me directly, just contact me in the usual way. Okay, see ya.